Welcome to the webinar about topology optimization and generative design. My name is Urs Simmer from GIA Informatik. I'd like to show two products, one product from PTC, a new product called GTO and GDX, and I'd like to compare it a little bit with a product which is longer on the market. It's from CAESS, Protop, and we'll see what are the differences of these two products. Here is the agenda. First, I'd like to talk a little bit about me and the company I'm working for. Then we're talking about the new solutions from PTC. We're talking about GDX and GTO. And then, of course, we're doing some live presentation with these products. Later on, we'll see the topology optimization product from CAESS, and also we'll see there a live presentation where we are going to optimize also the same bracket here. And at the end, we'll have a little slide about the comparison of these two products. If you have any questions, feel free to use the question panel, and at the end of the webinar or in between, if there is some time, I'd like to answer your question. In case we do not have any time, I will answer your question later on tomorrow with an email. So let's start to talk a little bit about me. My name is Urs Simmer. I'm the simulation guy here at GIA Informatik. Before I joined GIA, I was working 20 years for PTC, and my focus was and is still on the simulation products. Today, not in the call, is our salesperson, Daniel Losley. If you have any question about prices, test licenses, that kind of stuff, you can contact him here. Myself, I also have a YouTube channel. If you like to join this channel, feel free to subscribe. Okay, some words about GIA Informatik. GIA Informatik is a reseller with about 140 employees. We belong to a bigger company called Müller-Martini Group, and we are located in the middle of Switzerland. We have, let's say, three parts here. One is doing some SAP solutions, the other one is doing IT services, and 10 people are in the department for the CAD, CAM, CAE products, and of course for the PLM products. Our, let's say, main partner in the PLM CAD space is PTC, but we also have products from other PTC partners, and one of these products we'll see today. So personally, I'm doing sales support, workshop consulting with PTC products, mainly with the PTC cryoparametric products. And beside that, I'm also responsible for the product we're going to see this afternoon, Protop from CAESS, a Slovenian company. We also have electrical clearance and creepage analysis from eLaborate. We are selling solutions from TechSoft, Software Factory, and P&V Software. And we also have, let's say, a training center in Oftringen here. Okay, that's all about me and the company, and I'd like to start with the new product from PTC, which came out 2 weeks ago with the 7.0.20 version. We got, let's say, a new product called GDX, Generative Design Extension, and since half a year we have, let's say, GTO, Generative Topology Optimization, So those two products are only available in the 7.0 version of Creo Parametric. What's the strategy of PTC with these two products? By the way, these products came from other company because PTC bought 2 years ago a company with the name Frustum, and this company's products were these generative design capabilities, and now they are implemented in the Creo Parametric product family. So since 7.000 we have GTO, and GTO is, let's say, topology optimization capability with the Frustum technology, and on top of that we can have now the new product called GDX. As you can see here with that symbol, it's a cloud solution, and in the GDX solution we can do, let's say, cloud computing. We can test many variants of our topology optimization products. Okay, this is a new product. This is only available in 7.020. Okay, what's the GTO? So I will show later the GTO product, the desktop solution. With this solution we want to create, let's say, very powerful products with the help of loads and constraints and the manufacturing process we are going to choose. We are creating, let's say, different kind of products, different shapes, and in the end we want to have the most powerful shape of that one. And this GTO supports us within the Creo Parametric solution. On top of that one, here is also a link where you can see later on a movie which is showing this GDX product. With the GDX we have, let's say, a cloud solution. As far as I know, the cloud is based on the Onshape product from PTC, and in this cloud solution we can test many variants of our topology optimized products by, let's say, changing materials, by changing the sizes, by changing materials, by changing the machining option, how this product is produced. Is it a 3D printed component? Is it a forged component? Is it a casted component? Okay, this is new, only available in 7.0.0. But both of these products have the same target. They want to optimize and deliver high performance products, and of course with the help of the cloud we can do much more variants, and in the end we can decide, we can choose, let's say, the best one of that one. But the technology behind the two products is the same. This is the Frustum technology, the generative optimization technology, and in the cloud solution, yes, you can test many of that variants here. And I'd like to show you now how this product is working within Creo Parametric. So the product GTO is available in 7.0.0, and the GDX, which I can only show with a movie, is available in 7.0.20. We will optimize a product with the help of a design room, with the help of loads and constraints, and at the end we'll also see then a simulation with Creo Simulation Live powered by ANSYS. So let's go for the Creo Parametric environment here. I already loaded a nice port, and as you can see here in the model tree, we have also new capabilities in Creo Parametric called multi-body. So nowadays we can create parts with more than one body inside, and we can also assign different materials to that bodies. And one application of that multi-body is the topology optimization. And in the topology optimization I want to create later on, let's say, fixed geometry and that kind of stuff, and therefore I'm using the multi-body technology. I'm activating the second body. It's empty right now because all the other features are belonging to the first body, and here I just create here, let's say, my new fixed region by creating here some extrusion. I'm taking here some existing geometry. I'm doing here additional geometry, a circle, and with that circle with a diameter of 25 millimeters, I'm going to create, let's say, a fixed region. I want to do here a protrusion until the surface, and of course now in that region I have, let's say, double material. I'm doing the same here on that part of my component. I'm creating again extrusion. Okay, first I'm projecting existing geometry. I'm doing here additional geometry with a line. Okay, I'm sketching some arcs. Okay, another arc here. And I'm doing the final line here, changing the dimension to 15 millimeters. Okay, and my new body here is done. Okay, so now we can see here in our model tree we have a body with, let's say, the design room, and here we have a body with the fixed geometry. And in the application generative design, we can now build our topology optimization model. Up here we can build our model, we can do some settings and that kind of stuff, and here in the model tree we're getting some information about our models. And of course we also have access to our model tree here from Parametric. We can change here some options. Now here I switched on that at the end I want to have a final FEA simulation with the Frustum solver, and here in that region I can I can add my design criteria, and what else? Here we have the troubleshooter and so on. So I did nothing, everything is yellow, and I'm starting now to define my design room starting geometry. I'm selecting that one. The starting geometry will be hidden. I'm doing here some fixed preserved geometry. I'm selecting that body from Parametric. It's changing the color so I can see this is fixed geometry. Here I would also have the possibility to create excluded geometry. Right now I do not use that kind of stuff. And now I'm adding here some constraints. I'm going here for that surfaces, and fixed constraint geometry is done. Here in that region I'm adding some loads. I want to bring in a load of 1000 Newton in that direction, and on that surface I'm creating in the other direction also 1000 newtons. Okay, we can see here we only have one symbol left about the design criteria, and now I'm going to define the design criteria. Here in that region the study settings can also be applied. I set here my settings to a little bit more speed because I'm using an old laptop from Lenovo. It's a model P50. It's about 4 years old, my laptop, okay. And with the design criteria, I can define what's my target. I want to reduce, let's say, the weight of my part or the volume of my part down to 25%. Here I could choose also maybe the weight in kilograms. And beside that, very important, I can add some design constraints. Here I can define parting lines, or I can do some milling components here. In our case, I'm just defining a planar symmetry with the help here of that datum plane called right. And I'm adding here an additional constraint, so-called material spreading. This is just, let's say, influencing the thicknesses of my beams. I'm setting it to a middle range here. Okay. Now we can see there is no more symbol here left, so I'm able to start my analysis here. I could send it to the cloud here with that symbol, therefore I need a login at PTC. Unfortunately, I didn't get a login so far, but I can show you the behavior of that GDX version later on in a little movie. Therefore, we are doing on our desktop solution with GTO, we are doing here our optimization study. I started the optimization. You can see here the symbol that now the model will be filled. We can see we have a weight of about 900 grams on our component, and now GTO is starting with the frustum technology to optimize this part. Here we can also see the material we were choosing. We have some additional information about optimization strategy, about our limit target or volume limit target, and in our main window we see the growing of our bionic structures here. Unfortunately, we cannot see during this optimization, we cannot see the, let's say, the stress results or the deflection results. This is only available at the end of our simulation. This simulation will last about here 3 to 4 minutes, depending on what's my workload on the computer with other applications, and therefore I will tell you, okay, you can also ask some questions. Please use the question panel if you have any questions. I can answer them now or at the end of the webinar. And during this optimization process here, I show you also the solution with the help of a little movie, the solution GDX here. In GDX, when you're logged in, you have here the possibilities to set up your model. You can set up the design variables, what kind of materials you like to use, what production strategy you like to have. Do you want to mill it? Do you want to cast your component? You can also, let's say, modify the dimensions of your parts, and at the end of this process here you're getting the solutions, maybe 100,000 of that solution. The powerful cloud solution is doing that for you. You can choose then different variants, and you can compare them. You can have a look at the performance of that part. What are the deflections? What is the weight? What is, let's say, the von Mises stress? And in the end, you can say, okay, I like to choose that one. And then this component will be downloaded to your Creo parametric session. It will be reconstructed. Normally it doesn't work that quick. We'll see that later on, and then you can do some further testing on that component, that you can do some additional features constructing on that component. That's the way how this GDX solution is working. In the meanwhile, we see, okay, our optimization is still running here. We spent around 3 minutes, okay, and I hope, crossing my fingers, this optimization is coming to the end. We can see right now here a very interesting bionic structure, okay, and we see that our target we were setting is now fulfilled. We are near 25% with our volume, and I hope now this optimization will be finished in the next seconds. Okay, I'm checking the questions. There are already some questions. What's the main difference between topology optimization and generative design? Most of our customers don't see any difference. Yeah, it's quite hard because behind, let's say, the frustum technology is the frustum solver, and PTC or especially frustum doesn't tell a lot about the technology behind it, but it's more or less the same as topology optimization. Here, good luck for me, it lasted 5 minutes. Never lasted that long, but anyway, now we have our topology, and we can also have a look at the results. What is the stress distribution? Where are the stress peaks here? We can have a look, of course, at the stress in megapascal. We have stresses around 85, 90 megapascals, and we can see here the displacements around 0.1 millimeters. It's also possible then to animate the behavior of our component, so we see deflection and stresses. In order to check, let's say, the analysis here. Oh yes, now we can see here the deflections. And at the end of the day, we can also reconstruct our component here with the generative design button. PTC created a nice solution which is, let's say, reconstructing the component automatically. So I'm going to generate that one, and I'm creating a new part called Chuck. Oh, it's writing like that. Okay, and now Cryoparametric is taking a template. It's taking here my fixed areas, this kind of stuff. And it's taking here my bionic structures. With the bionic structure, it's building, let's say, a freestyle surface. And in the end, these 2 parts, they are taken by Cryoparametric, and they will be merged together. Okay, this is live presentation. Before I used 5 minutes to do the topology optimization part, and now I think it also takes a minute to build this part here. In the first version of GTO, this part was not always successful, but within the new version, PTC really improved this process, and we'll see, cross my fingers, that this step will be successful. Okay, now it's coming to the end. It's merging the parts. It's building a volume, and quite soon I can see here my new component. Of course, here with my in my layer tree, I'm hiding my curves, and I can see here quite a nice part. Here is the reconstruction. Here we see, let's say, the freestyle surfaces. Of course, when I'm going to the detail of that component and I'm looking here from top, okay, and I'm checking maybe that surface, I can see, okay, the component is not totally symmetric, and really if I'm going into detail, sometimes you see also, yes, let's say a little bit strange surfaces here, but it's, let's say, for first shot, it's done quite nice, and we can also use that new constructed topology in Creo Simulation Live for an analysis here. So the forces and the constraints will be automatically applied to the new constructed model, and then in Creo Simulation Live you have the possibility to show stress results, that kind of behavior. Of course, these results are a little bit better than, let's say, the results from the frustum solver, but we see, okay, the stress is more or less the same. It's around 94 megapascal. That's a process using GTO. I think it's well done from PTC, very well integrated, and I would say quite easy to handle, quite easy to use. We're going for, let's say, the next product. So we saw right now GTO and the movie of GDX, and now we're going to have a look at the, let's say, traditional product called ProTop from the Slovenian company CAESS. ProTop is a, let's say, traditional topology optimization tool which can be used with input text or information from Creo Parametric, from SolidWorks, Siemens NX, or CATIA. And let's say this product has also a little bit more advanced options. In this product is also possible to use here these lattice structures. You can do nonlinear contacts, you can do nonlinear material behavior, all that kind of stuff. And you'll see this is a standalone product, and yes, in the new version we also have some new highlights, especially, let's say, the smoothing process of the surfaces is becoming nearly perfect right now. Okay, let's have a look at the same bracket, how, let's say, the workflow is with ProTop. We will also start with the model in Creo Parametric, and we are going to optimize it, and at the end of the day we are bringing back the geometry to Creo Parametric, and we're doing an analysis not with Creo Simulation Live, we're doing this with Creo Simulate, the standard product of PTC. Okay, let's go for the next session here. Here is, let's say, the same shape in Creo Parametric, but we do not use here the generative design capabilities. We're going first for Creo Simulate, and in Creo Simulate you also have the capability to switch to the FEM mode. FEM mode is just creating, let's say, models with H elements, with the small elements, and these elements will be used by ProTop for the topology optimization. Here I already set up, let's say, the model. I created the volume region more or less in the same way as I showed before, and I created here a surface region for my loading. I constrained my component, I loaded it plus minus 1000 Newton in both directions, and here a little bit special here, I created two materials here. It's titanium, aluminium, and it's with the same properties. The only difference is the name here, and with that different name I just said, okay, the fixed region has a a material named underlined fixed, and let's say the free region is the normal material, and then Protop later on will recognize this feature as fixed and free regions. In addition to that, I set it up here a mesh control. I set the maximum length of an element is 1.775 millimeters, and I created here a load set. By the way, both of the programs can use several load sets. In this demonstration, I'm just showing one of them. With the help of here, maybe you know that one, under tools, there are some auxiliary application. I will bring in here my Protop gateway. I did that with a Met key. Okay, I'm pushing that Met key. I'm getting here a new button, and with this button here, the component will be meshed. There will be written out a, let's say, output deck. Protop will be started, and this output deck will be loaded into the Protop 6.1 version. We saw the mesh, and now Protop is starting, and it's coming up, and the source will be imported. So it's a, let's say, one-way gateway, and the feedback of the optimized geometry will be shown later. It will be done with STL or with OBG. So here we have a easy to handle user interface of Protop. We also have here a nice documentation with meaningful help, with meaningful pictures and so on. And I think also the handling of that solution is quite easy to learn. We have here a session manager to take care about our variants of our topology optimization. Here we can see the materials I was talking about. I have here the fixed region, and here I have the free region. Here I could also change, let's say, this type. Is it fixed? Is it free? Here I can also have a look at my load cases and so on. And in this section here with the technological constraints, I can also, let's say, bring in plane symmetry, milled, is it casted, all that kind of stuff can be done. And here again, if I'm going for the help, I can see really what's behind this option. Okay, I'm creating here a plane symmetry as before. I just say this volume here should be symmetric regarding to that purple plane. Okay, and this is done. And I'm also done, let's say, with the setup of my model. I'm going here for my topology optimization. I'll say my target is now 25% of the free volume. I want to do it, let's say, this topology optimization quite aggressively. So I was moving the slider up here, and now the analysis is starting. And during the analysis, I can have a look here at the displacements, at von Mises stress, main stresses, or just can have a look at the geometry here. Now we see, okay, I'm switching here to the stresses here, and during the optimization I can see, okay, this is my stress level, and it's also showing me this cutting away of the material. In that area I can see what's the actual weight of my component. I can also switch here the target during my optimization process. I can change here the aggressivity, all that kind of stuff can be done. I also have the capability to do some cross-section during the optimization. Okay, the cross-section can be moved here. I would say it's quite easy to control the topology optimization during the run and to influence it, to stop it, to do some new variants starting at that point. This is quite easy to fulfill with this optimization. Okay, we see right now the bionic structure is growing. It's cutting away the material not needed, and depending on my aggressivity and depending on the number of elements here, the cycle time is coming down more and more, because let's say the volume of my optimized component is going down and down and down. So every 7 seconds I'm getting, let's say, new instance here, and I can see right now which are the regions needed for, let's say, optimal stress or strain behavior. We are quite close right now to 25% here. We have a weight of 41%. We see also here the volume. I forgot to measure the volume of the old variant with GTO, but the target will be around 50,000 cubic millimeters. And now we see, okay, we are around 28%. I'm going further down. Going here, changing my target. I want to cut out more, but I want to, let's say, take out here a little bit more of the aggressivity here. So I will move that slider a little bit to that side. We see in that region, okay, it's taking away this area there, this bar. Now it's done, it's history. I'm going further down. I'm changing my aggressivity a little bit, of course, and here now I can see the behavior of my component. I'm going a little bit further down because I'd like to get rid of maybe of that bar here. Okay, now it's also history. I'm adding again some material. I'm going up here again, and I can see right now, oh, this, let's say here in that diameter, we do not have enough elements to have, let's say, very, very good results. Therefore, I'm pausing my analysis. Okay. And I want to bring in some more quality to my component. I'm just going back for a mesh refinement. I'm doing the little analysis of the actual mesh. I'm bringing down a little bit those edge sizes. In the end, I want to use not more than 7.1 gig for the mesh refinement, and I'm starting the mesh refinement. A new session will be done, so I have the old coarse mesh, I have the old shape, and let's say in my session manager I can now start to build variants with the technology. When we're looking at that area here, we can see, okay, mesh refinement is quite nice, not done yet, it's still running mesh refinement. I hope it will be done quite soon. Be patient. Now it's done. Okay. And now I can go back for my optimization. I'm going back for topology optimization. I say, okay, I want to go a little bit further down with my volume to around 9%. It's taking the optimized room with the new dense mesh, and it's restarting, let's say, the optimization. Of course, here I can go in and say, okay, my stress level should be between 0 and 100 megapascal, and we can see here in that area the color is red, a little bit orange. The stress is right now around 80 megapascal. And now Protop is doing with the dense mesh here, it's doing an additional topology optimization, and we see right now we are around 10.8%, and in the end I want to have here, yes, I'm very close, I want to have 50,000 cube millimeters. I'm extremely close to that one, and now it's, let's say, just moving around a little bit those elements here, let's say, to really optimize my component. And we'll see that the target convergence and the stability is quite good. Within about another minutes, our optimization will be done. And when we're looking at the optimization time, we are in the same range as before with GTO. They were used, I remembered, 5 minutes, and now we are around 5.5 minutes. And here we could see, we could influence, let's say, our optimization path. Now I'm stopping my optimization. It's nearly converged. This one is stopped. Of course, here I could type in, show me 85 megapascal, and I can see right now, yes, here it's around 85, this stress here. So let's say the stress quality, depending on the dense mesh here, is very, very good. And now we want to bring back those new shape to our CAD system, to cryoparametric. Therefore, we're going for the export area. In that export area, we can create some surfaces. Okay, and very new here, we have a new smoothing capabilities within ProTop. I can expand here the bandwidth. That means all the dark blue area will not be smoothed. When I increase that one, you see the dark blue area is getting smaller, so that means the blue area will be smoothed, and I can go in here and say, okay, I want to remove some peaks. I want to smooth the surface a little bit more. Maybe I'm zooming in a little bit more, then you can see here the incredible smoothing capabilities. I'm going to refine my triangles. I'm going to simplify them a little bit more. I'm removing peaks again, smoothing surfaces, refining triangles, and just doing here this loop twice or 3 times, and then at the end I say, okay, I want to simplify it a little bit until I get, let's say, that shape here. I would say this is quite perfect. I would say this can be used directly for 3D printing. And if I want to do 3D printing directly on this geometry here, I will use here the STL format. I'm going here for exporting that surface as a STL. I call it stl.stl, very meaningful. Okay, it's in the right directory, and now I want to also, let's say, prepare the surface for creating a B-rep surface in the CAD system. Therefore, I'm going to simplify here my triangles, maybe to that quality here, and I'm going to export that surface as a OBJ file. OBJ is a wavefront format and can be used in many CAD systems. And one CAD system is cryoparametric. I'm back in cryoparametric, and I'm going to open here, not the shock. I want to open first the STL file I created. This can be used, let's say, for reconstruction or for sending to the 3D printer. Or I'm going to import right now to my component called URS. I'm going to import the OBJ file with the freestyle option. This is free for everybody, the freestyle option. We can also, let's say, import here OBJ files. This one is not free for all, the reconstruct, but the import here, this one is free. And I'm going to import the OBG file I was writing out 30 seconds ago. And of course, this OBG file can be modified. You can take away some regions of this OBG file. It would have make sense to use maybe only half of that one, because I want to create a symmetric model, then the performance would also be a little bit better. But let's say for importing that surface, I'm really surprised how quick that works. So it takes another 10 seconds to be able to manipulate this data. Now I can have a look maybe from right. And now here I can, let's say, select those triangles here. Behind, let's say, that surface are triangles, and I'm going to select them. Okay. Here I selected too much. I can take it out here again, this point, and I want to use maybe this triangle and this triangle here. And in that area I want to use maybe that triangle, this here and this here. Okay. Should I take that one? No, I leave it. So now I want to make later on these edges of that triangle, so I want to make them sharp again. So I'm looking now from front to my component. I'm selecting, holding down the control key, additional surfaces here, or triangles, those on top here. And further down, holding down control key, I want to use that one here. In 3D, I've selected now all, let's say, the flat surfaces, and I want to make them sharp. The edges should be sharp now. I'm switching, let's say, this value from 0 rounded to 100 totally sharp. And now my edges or my rounds on that triangles are becoming edges. And now I'm accepting those surfaces, and now my freestyle surface will be saved in my cryoparametric environment. I have a BREP shape of that one, and I can build later on a volume with that surface. This is also taking 10-20 seconds, and in the meanwhile I'm going to have a look at the question panel. Somebody, I have faced failure in export. Any tips to make it better? I would say the tip to make it better, I think this is GTO. You must use 7.0.20. 7.0000 by exporting these surfaces. This is really a nightmare, but quality improved in 7.020. Okay, it's still on the run. Surface is not done yet. Now it's nearly done. I can see still the stop button here. Okay, now it's done. Now I have my surface, and now I can say, okay, I'm selecting my surface here, surfaces. Come on, and I'm building here a volume out of that. And I guess within 1 minute I have now my volume, and I can use that volume, sending it to the 3D printer, doing some additional stuff with that new volume. I'm checking again here the question panel. Thierry Simon, is it also possible to export only the optimized shape from ProTop? Yes, this is possible. When I was exporting that one here, or creating here by creating the surfaces, here I can say, okay, I want to, let's say, exclude these fixed surfaces, and then only the, let's say, the free room will be taken, and I can, let's say, smooth that surface and export that surface, and doing, let's say, the merge maybe by hand in Creo parametric. I guess in the meanwhile, here, yes, the 3D model is done, or nearly done, and now I could go with that model to Creo Simulation Live, Creo Simulate. Here with that model, which was imported, of course I have to add the constraints and the loads again to, let's say, make a validation of that component. And I will show you later on the results in Creo Simulate of a version I analyzed yesterday. The analyze time in Creo Simulate is around 20 minutes for that model, because we will have quite a dense mesh there. Okay, it's done here, the model, and I can show you of this analysis. I can show you the results here with simulate results. I can show you the von Mises stresses of that component I analyzed. I think it was yesterday. Okay, this is loading here, results, and we can see right now the results in Creo Simulate. And of course here we see, okay, the results are also around a few megs, 89 megapascals. Okay, it's more or less everywhere the same stresses. But yeah, that brings me to the end of my live presentation, and I'm switching here back to my PowerPoint. This PowerPoint will be distributed to you tomorrow, and here I just created a small slide where I compare those two products. On the left side we see the GTO GDX solution. I think it's important to know this is only available in Creo Parametric 7.0, 6.0, 5, and so it's not available there. I think it's quite good, as we saw the integration in Creo Parametric, it's nearly perfect. Also the surface reconstruction now works in 7.0, quite good. And you'll have, let's say, the possibility to use also the cloud solutions. A little bit hard is it to find any information about the technology behind this Frustum solver. For me it's a little bit the black box algorithm. PTC is talking about artificial intelligence, but you'll find nowhere any documents about what's behind that one. I mean the optimized components are looking quite interesting, but it would be great to have a little bit more information about that. In GTO GDX there is no lattice, no shell features available, no non-linearity is available. Let's have a look at the CAESS. I mean, you can feed CAESS with input text from different CAD systems. It's a traditional topology optimization. You can read the documents, what's the technology behind it. Right now, the CAESS solution has a little bit more technological constraints. The surface reconstruction, it's not, let's say, that easy as in Creo Parametric, but at the end of the day, I mean, we saw that surface, we saw that here the surface is not really symmetric. We saw here there are, yes, a little bit shaky surfaces. At the end, if you want to really create a components which can be machined, I would say you have to reconstruct the component. For 3D printing, it's perfect, or for doing some testing, it's perfect, this solution from PTC. And also this solution from Protop, it's usable, and you can also do 3D printing directly with STL files. If you need any BREP representation of your components, it's also possible to do that with Protop surfaces. Yes, this brings me to the end of the webinar. If you want to test that one, topology optimization, Creo simulation live, or mechanism, and what else, we're doing also some workshops with that one. During the COVID time, we're doing them also online. Please contact us if you have any need. You have here a link to show the timetable of these workshops. And at the end, we have maybe 5 minutes time, or only 2 minutes time for additional questions. Question is, do you think that new users should have already used some previous experience with GTO? I think a user for both of these solutions should be able to do, let's say, a simulation with Creo Simulate or Creo Simulation Live. A user should have knowledge about FEA, but it must not be, let's say, deep knowledge of FEA, but they have to know what's a constraint, what's a load, and that kind of stuff. Yes, there are some more questions in the question panel. Due to the time, I will not ask them. I will write an email to you tomorrow and to answer your questions. At the end, I'd like to thank you for your time. I hope you have now an impression about the capabilities of topology optimization, generative design in the CAD environment, especially in the PTC Creo parametric environment. You have an impression about the integrated product GTO and GDX, and you have also an impression about the external products from CAESS called Protop. So in the end, again, thank you. Have a good time. Stay at home and stay healthy, and see you soon. Bye bye. Auf Wiedersehen.